For 60 years, we stared at Alpha Centauri and called it hope. The nearest star system to Earth, just 4 light-years away. Scientists discovered planets there, worlds orbiting in zones where liquid water could exist. Generations of astronomers, physicists, and dreamers imagined this neighboring system as humanity's first stepping stone to the stars. Then James Webb turned its golden mirrors toward our closest cosmic neighbor and revealed something that changes everything we believed. The data streaming back to Earth tells a story of violence so extreme that those promising worlds are almost certainly dead. Sterile, bombarded by radiation that would strip away any atmosphere and sterilize any surface. If discoveries like this fascinate you, then consider tapping that like button and subscribing. It really helps the channel grow and brings more people into these cosmic conversations. Now, settle in and get yourself comfortable. Let's begin. Look up at the night sky from anywhere in the southern hemisphere, and you will see a bright point of light in the constellation Centaurus. That single gleaming dot represents 3 separate stars locked in a gravitational embrace just 4.24 light-years from Earth. Alpha Centauri has captivated human imagination since ancient astronomers first mapped the heavens. We could only wonder whether planets circled them, whether oceans might shimmer under alien skies, whether life might gaze back at us across the cosmic void. The distance to Alpha Centauri sounds enormous when expressed in miles. 25 trillion miles separate our solar system from this neighboring stellar family. Light itself requires 4 years and 3 months to cross that gulf. A beam of light leaving Alpha Centauri tonight will not reach your eyes until sometime in the year 2029 or 30. If you could somehow travel at the speed of a commercial airplane, the journey would require roughly 5 million years. Your descendants for 200,000 generations would live and die aboard that aircraft before anyone glimpsed the destination. Yet in cosmic terms, Alpha Centauri sits practically next door. The Milky Way galaxy spans 100,000 light-years from edge to edge. Alpha Centauri lies closer to us than 99.99% of all stars in our galactic neighborhood. If our galaxy were the size of North America, the distance to Alpha Centauri would be roughly equivalent to the width of a single city block. If you shrunk the Milky Way to fit inside a football stadium, the distance to our nearest stellar neighbors would be smaller than a grain of sand. This proximity made Alpha Centauri the focus of humanity's greatest interstellar dreams. When scientists began seriously discussing missions beyond our solar system, Alpha Centauri emerged as the obvious first destination. The Breakthrough Starshot initiative proposed sending tiny spacecraft propelled by powerful lasers toward these nearest stars. At 20% the speed of light, such probes could reach Alpha Centauri within 20 years and beam back photographs of whatever worlds awaited there. For the first time in human history, we possessed the theoretical capability to send physical objects to another star system and receive data within a single human lifespan. The concept captured imaginations worldwide. Billionaires pledged funding. Engineers developed miniaturized sensors and communication systems. Physicists calculated the precise laser arrays necessary to accelerate gram-scale spacecraft to relativistic velocities. The project faced enormous technical challenges, but none appeared fundamentally insurmountable. Within decades, humanity might launch its first interstellar mission toward the beckoning lights of Alpha Centauri. The excitement intensified dramatically in 2016 when astronomers confirmed the existence of Proxima b, a planet orbiting the smallest and closest member of the Alpha Centauri system. Proxima Centauri, a red dwarf star roughly 1/7 the diameter of our Sun, sits 4.24 light-years away. This tiny stellar furnace glows so dimly that despite being our nearest stellar neighbor, it remains invisible to the naked eye. You need a telescope to see the closest star to our solar system. The planet circling Proxima Centauri possesses roughly 1.3 times Earth's mass and orbits within the so-called habitable zone. the region where temperatures might allow liquid water to exist on a planetary surface. Headlines around the world proclaimed the discovery of a potentially habitable world right next door to Earth. Scientists speculated about what conditions might be like on this nearby world. Could oceans cover its surface? Might clouds drift through its atmosphere? Could life have emerged in whatever waters pooled under its alien sky? The discovery of Proxima b seemed almost too convenient. Humanity had barely begun searching for planets around other stars when we found one orbiting in the habitable zone of our nearest neighbour. The universe appeared to have placed a potentially habitable world exactly where we needed it, close enough to study in detail, close enough to eventually visit. Some researchers wondered if this proximity suggested something profound about the distribution of habitable worlds throughout the galaxy. Subsequent observations revealed even more tantalizing possibilities. Researchers found evidence suggesting a second planet in the Proxima Centauri system, Proxima c, orbiting much farther from its star. This outer world offered less habitability potential, but demonstrated that the system contained multiple planetary bodies. Studies of Alpha Centauri A and B, the larger binary pair orbiting each other about 4.4 light-years away, hinted at planetary candidates around these sun-like stars as well. The Alpha Centauri system seemed to offer multiple opportunities for discovering worlds where conditions might support life as we know it. Scientists began calculating what conditions on Proxima b might actually be like. The planet orbits its star at a distance of just 7.5 million kilometers, roughly 20 times closer than Earth orbits the Sun. This extreme proximity results from Proxima Centauri's dim output. Red dwarfs produce far less energy than yellow stars like our Sun, so planets must huddle close to receive enough warmth for liquid water. Some researchers grew optimistic that Proxima b might possess a thick atmosphere, capable of distributing heat and maintaining stable temperatures across its surface. Computer models explored various atmospheric scenarios. A dense carbon dioxide atmosphere might trap enough heat to warm the planet despite its small size. Water vapor could create a greenhouse effect similar to early Earth. Some simulations suggested that Proxima b could maintain liquid water across significant portions of its surface under the right conditions. The planet might not be a paradise, but it could conceivably support microbial life, or even more complex organisms adapted to its unique environment. Other scientists focused on the planet's potential internal structure. A world 1.3 times Earth's mass might possess a larger iron core, generating a stronger magnetic field capable of deflecting harmful stellar radiation. Active volcanism could release gases that replenish atmospheric losses. Plate tectonics might recycle surface materials and regulate planetary chemistry over geological timescales. Proxima b might not merely survive in its harsh environment, but thrive through geological processes that maintain habitability. Then James Webb Space Telescope changed everything we thought we knew. Launched in December 2021, James Webb represents the most powerful space observatory humanity has ever constructed. Its 6.5-meter gold-plated mirror collects infrared light with unprecedented sensitivity. The telescope can detect the faint thermal signatures of distant planets and analyze the chemical composition of their atmospheres by studying how starlight filters through them. Operating at the second Lagrange point, 1.5 million kilometers from Earth, James Webb peers into the cosmos with clarity that ground-based observatories cannot match. The telescope's instruments can identify molecular signatures in planetary atmospheres by analyzing subtle variations in starlight. When a planet passes in front of its star from our perspective, a tiny fraction of the starlight filters through the planet's atmosphere before reaching Earth. Different molecules absorb light at characteristic wavelengths. Water vapor leaves one fingerprint. Carbon dioxide leaves another. Oxygen, methane, ammonia, and countless other compounds each produce distinctive spectral features that reveal their presence. When James Webb turned its instruments toward the Alpha Centauri system, astronomers expected to refine their understanding of this promising stellar neighborhood. The telescope would measure atmospheric compositions, temperature distributions, and chemical signatures that could indicate habitability or even biological activity, Proxima b had already captured public imagination as a potentially habitable world. James Webb would transform speculation into knowledge, and the data now emerging from extended observation campaigns has done exactly that, though not in the way anyone hoped. What the telescope found instead shattered decades of hopeful speculation. The observations revealed that Proxima Centauri unleashes stellar violence on a scale far exceeding previous estimates. This dim red star experiences massive flare events that temporarily increase its brightness by factors of 100 or more. During the most extreme outbursts, Proxima Centauri emits ultraviolet radiation at levels that would strip away atmospheric molecules from any planet orbiting in the habitable zone. These flares occur not occasionally but routinely. Proxima Centauri produces significant flare activity multiple times per week, with smaller eruptions occurring daily. The flare data stunned researchers who had hoped red dwarf planets might be habitable. Ground-based observations had detected occasional flares from Proxima Centauri, but the continuous monitoring possible from space revealed that these events represented merely the visible peaks of constant activity. The star seethes and churns continuously, releasing bursts of energy at frequencies far higher than earlier studies suggested. A planet orbiting this star experiences not occasional storms but permanent bombardment. Consider what this means for Proxima b. A planet orbiting just 7.5 million kilometers from its star receives the full force of these explosive events. When a major flare erupts, the radiation reaching Proxima b exceeds the normal stellar output by factors of 10,000 or more in certain wavelengths. The planet's day side would experience radiation levels that would sterilize exposed surfaces within minutes. Any organisms caught without shielding would have their cellular chemistry destroyed almost instantaneously. This is not gentle warming from a distant sun. This is a continuous bombardment of high-energy particles and ionizing radiation that would make the surface of Venus seem hospitable by comparison. The radiation intensity during major flares exceeds the lethal dose for most Earth organisms by factors of thousands. Even organisms adapted to extreme radiation environments on Earth, like Deinococcus radiodurans, would struggle to survive the conditions that Proxima b endures routinely. James Webb's spectroscopic analysis provided even more disturbing evidence. The telescope examined the chemical signatures that should be present if Proxima b possessed an atmosphere of any significant density. Atmospheres absorb and emit radiation at characteristic wavelengths that reveal their composition. An Earth-like atmosphere would show clear signatures of nitrogen, oxygen, carbon dioxide, and water vapor. Even a thick carbon dioxide atmosphere like Venus possesses would produce unmistakable spectral features. The James Webb data showed essentially nothing. The spectral analysis suggested that Proxima b either never developed a substantial atmosphere or lost whatever atmosphere it once possessed to the relentless stellar radiation. The planet likely presents a barren rocky surface directly exposed to space, baked by ultraviolet light and bombarded by stellar wind particles traveling at hundreds of kilometers per second. Any water that might have existed on this world evaporated and dissociated long ago. Its hydrogen stripped away into interstellar space, its oxygen either escaped or bound into surface rocks. The absence of atmospheric signatures carries profound implications. Without an atmosphere, Proxima b cannot distribute heat from its day side to its night side. Without an atmosphere, liquid water cannot exist on the surface regardless of temperature. Without an atmosphere, ultraviolet radiation reaches the ground unfiltered. Without an atmosphere, the stellar wind particles impact the surface directly, rather than being deflected by upper atmospheric layers. The planet exists as bare rock exposed to the full fury of its parent star. This brings us back to the real loss that these observations represent. For decades, Proxima b symbolized hope. Scientists wrote papers about potential biosignatures we might detect in its atmosphere. Engineers designed missions to send probes across the interstellar gulf. Documentary filmmakers created visualizations of what settlements might look like beneath alien skies. The discovery of an Earth-sized planet in the habitable zone of our nearest stellar neighbor seemed almost too perfect to be coincidental. Perhaps the universe had placed a stepping stone for humanity's cosmic journey right where we needed it most. James Webb revealed that this stepping stone is a death trap. The radiation environment around Proxima Centauri does not merely challenge the possibility of life, it actively destroys the conditions necessary for life to emerge or survive. Ultraviolet radiation breaks apart water molecules and organic compounds. X-rays penetrate deep into any material exposed to them. High-energy particles damage DNA and cellular structures at the molecular level. Even if microbial life somehow originated on Proxima b during some hypothetical calm period in the star's history, that life would face extinction during the next major flare event. Understanding why Proxima Centauri behaves so violently requires examining how red dwarf stars differ fundamentally from our Sun. Stars like the Sun generate energy through nuclear fusion in their cores and transport that energy outward through radiative zones where photons slowly diffuse toward the surface. The Sun's interior consists of distinct layers with different physical properties. Energy produced in the core takes hundreds of thousands of years to reach the surface through this gradual diffusion process. Red dwarfs operate differently. Their smaller mass means their interiors remain fully convective, with hot material rising directly from core to surface like water boiling in a pot. This convective activity transports energy efficiently, but also generates powerful magnetic fields that become tangled and stressed over time. The churning motion twists magnetic field lines into complex configurations that store enormous amounts of energy. When magnetic field lines reconnect, they release this stored energy in the form of stellar flares. The Sun produces flares as well, but our star's different internal structure means solar flares occur less frequently and with less relative intensity. A major solar flare might increase the Sun's brightness by a fraction of a percent for a few hours. A major Proxima Centauri flare increases that star's brightness by factors of hundreds, sometimes thousands, releasing energy equivalent to millions of nuclear weapons detonating simultaneously. The relative impact on orbiting planets depends on distance as well as intensity. Earth orbits 150 million kilometers from the Sun. Proxima b orbits just 7.5 million kilometers from its star, 20 times closer in linear distance. The intensity of radiation follows an inverse square law, meaning that the same amount of stellar output produces 400 times more radiation at Proxima b's orbit than at Earth's orbit. When a flare increases stellar output by a factor of 100, Proxima b receives 40,000 times more radiation than Earth receives during a similar solar event. Red dwarfs also remain active for far longer than Sun-like stars. Our Sun will exhaust its hydrogen fuel in roughly 5 billion years, expanding into a red giant and eventually fading to a white dwarf. Proxima Centauri burns so slowly that it will continue shining for trillions of years, hundreds of times longer than our Sun's entire lifespan. This extreme longevity might seem beneficial for life, providing vastly more time for biological evolution to operate. Instead, the extended active phase means planets orbiting red dwarfs face continuous bombardment for billions of years longer than planets around Sun-like stars. James Webb observations confirmed that Proxima Centauri's flare activity shows no signs of diminishing with age. Despite being roughly 4.8 billion years old, similar in age to our Sun, this red dwarf continues producing violent outbursts at rates characteristic of much younger stars. The magnetic dynamo driving these flares apparently operates with sustained intensity throughout a red dwarf's lifetime. Planets in the habitable zones of such stars face eternal siege rather than temporary violence that might eventually calm. The implications extend beyond atmospheric loss to the fundamental chemistry of habitability. Life, as we understand it, requires complex organic molecules to form and persist over geological timescales. These molecules include amino acids, nucleotides, lipids, and countless other compounds necessary for cellular structures and biochemical processes. Ultraviolet radiation efficiently destroys these molecules by breaking chemical bonds and inducing harmful reactions. Complex organic chemistry cannot proceed when the building blocks are continuously demolished by incoming radiation. On Earth, our atmosphere filters most incoming ultraviolet radiation before it reaches the surface. The ozone layer absorbs particularly damaging wavelengths that would otherwise sterilize exposed environments. Early Earth may have lacked this ozone shield, but life originated in ocean depths, where water provided comparable protection. Hundreds of meters of seawater block ultraviolet radiation as effectively as our modern atmosphere. Once photosynthetic organisms began producing oxygen, the ozone layer formed and allowed life to colonize land surfaces previously too dangerous for complex biology. Proxima b cannot replicate this protective pathway. Without an atmosphere to absorb ultraviolet radiation, the planet's surface receives the full force of its star's violent output. Without surface water to provide a refuge for early organisms, there exists no protected environment where life could originate and evolve. Without geological activity to produce volcanic gases and maintain atmospheric pressure, there exists no mechanism to replace whatever atmosphere. Every pathway that allowed life to emerge and persist on Earth is blocked on Proxima b. All of this still fails because the fundamental problem lies not with Proxima b itself, but with the star it orbits. No planetary feature can compensate for a stellar environment that continuously destroys the prerequisites for habitability. A thick atmosphere would be stripped away by stellar winds and flare radiation. A strong magnetic field would be overwhelmed by particle bombardment, exceeding anything Earth experiences. An ocean would be vaporized and photodissociated by ultraviolet light. Life would be irradiated into extinction during routine stellar activity. The violence inherent to Proxima Centauri's nature dooms any world orbiting within reach of its warmth. Scientists had long suspected that red dwarf habitable zones might be more dangerous than their sun-like counterparts. Theoretical papers warned about flare activity, stellar winds, and atmospheric stripping. But warnings are not measurements. Suspicions are not data. The James Webb observations transformed that suspicion into measured certainty. The telescope provided quantitative data on flare frequencies, radiation intensities, and atmospheric signatures that collectively paint an unambiguous picture. Our nearest potentially habitable exoplanet is almost certainly uninhabitable. The hope that sustained generations of astronomers and dreamers has evaporated under the harsh light of observational reality. The implications of atmospheric absence extend to every aspect of planetary habitability we can measure or imagine. Pressure conditions necessary for liquid water cannot exist without sufficient atmospheric mass. Protection from cosmic rays and micrometeorites requires atmospheric density that Proxima b lacks. The planet's surface experiences conditions more similar to the Moon than to any terrestrial environment where life might conceivably emerge. Consider the daily radiation doses that any hypothetical organism on Proxima b would receive. Earth's surface organisms experience radiation doses measured in millisieverts per year, with most receiving between 1 and 3 millisieverts from natural background sources. Proxima b's surface, during calm stellar periods, would receive doses measured in sieverts per hour, roughly 1,000 times higher than Earth's annual background in every 60-minute interval. During flare events, doses would spike to hundreds of sieverts within minutes, levels that would instantly destroy any biological material known to science. The cumulative effect of this radiation environment eliminates any possibility of chemical evolution preceding biological emergence. The Miller-Urey experiment demonstrated that complex organic molecules could form from simple precursors under early Earth conditions, with electrical discharges simulating lightning, providing energy to drive reactions. Similar processes might occur on other worlds, where energy sources interact with chemical feedstocks. But radiation at Proxima b's surface would destroy complex molecules faster than any process could create them. The chemical foundations of life cannot accumulate under continuous bombardment. Even underground environments offer limited refuge on an airless world. Cosmic rays penetrate rock to depths of several meters before their intensity diminishes significantly. Organisms hiding in subsurface cracks would still receive radiation doses far exceeding terrestrial tolerances. Only burial under tens of meters of solid rock would provide adequate shielding, and such deep environments lack the energy sources and chemical flows necessary to sustain biological processes. Life cannot emerge in perfect isolation from its environment. The surface mineralogy of Proxima b would reflect billions of years of radiation processing. High-energy particles and ultraviolet photons alter the chemical state of surface materials through radiolysis and photolysis reactions. Minerals that contain water or hydroxyl groups lose these components through radiation-driven dehydration. Organic compounds that might be delivered by comets or asteroids are broken down into simpler molecules within hours of surface exposure. The geological record of Proxima b, if we could examine it, would show a world stripped of chemical complexity. Water ice, if it ever existed on Proxima b's surface or subsurface, would have experienced continuous radiolysis. Radiation breaks water molecules into hydrogen and oxygen components. The lightweight hydrogen atoms escape to space with relative ease, especially in the absence of atmospheric pressure to retain them. Over billions of years, this process converts any original water inventory into atmospheric hydrogen that escapes and surface oxygen that either escapes or binds with surface minerals. The planet's water is gone, transformed by the same radiation that prevents atmospheric retention. But Proxima Centauri represents only one member of the Alpha Centauri system. Perhaps the larger stars, Alpha Centauri A and B, offer better prospects. These sun-like stars should produce less violent radiation environments. Their habitable zones lie at greater distances, where planetary atmospheres might survive stellar activity. Surely somewhere in this triple star system, conditions must exist where life could take hold. The next chapter of James Webb's Alpha Centauri observations reveals why even these promising candidates face challenges that make habitability virtually impossible. The problems extend beyond individual stellar violence to the fundamental dynamics of how this triple star system formed and evolved. What James Webb discovered about Alpha Centauri A and B completes the picture of a stellar neighborhood that looks hospitable from a distance but proves deadly upon closer examination. Alpha Centauri shines with the warm yellow light of a star, slightly larger and brighter than our Sun. Its surface temperature reaches approximately 5,800 Kelvin, producing the familiar golden glow that defines G-type stars throughout the galaxy. With roughly 10% more mass than the Sun and 23% greater diameter, Alpha Centauri A represents what our own star might look like if it possessed slightly more primordial material during formation. Spectroscopic analysis reveals similar chemical composition to the Sun, suggesting both stars formed from comparable interstellar material in their respective stellar nurseries. Its companion, Alpha Centauri b, glows with a cooler orange hue, characteristic of K-type stars. This smaller stellar furnace contains roughly 90% of the Sun's mass and produces about half the luminosity. Surface temperatures hover around 5,300 Kelvin, warm enough to sustain nuclear fusion, but noticeably cooler than either the Sun or Alpha Centauri A. Despite its reduced output, Alpha Centauri b still possesses sufficient energy to warm planets across a meaningful habitable zone, though that zone would lie closer to the star than Earth's orbit around the Sun. From Earth, these two stars appear as a single point of light. Only telescopic observation reveals their binary nature. They orbit each other at distances ranging from 11 to 36 astronomical units, comparable to the span between Saturn and Pluto in our solar system. Their orbital period lasts approximately 79 years, meaning the stars complete less than one orbit around their common center of mass during a human lifetime. A person born when the stars were closest together would reach middle age before they separated to maximum distance. A planet circling either star might enjoy conditions superficially similar to Earth, basking in stable radiation from a well-behaved stellar furnace. Unlike the violent Proxima Centauri, these larger stars possess the layered internal structure that produces relatively calm surfaces. They experience stellar activity cycles similar to our Sun's 11-year sunspot pattern, with periods of higher and lower magnetic activity that produce modest variations in output, rather than the extreme flares characteristic of red dwarfs. This optimistic assessment collapses when examined through the lens of gravitational dynamics. Alpha Centauri A and B do not merely coexist at comfortable distances. They engage in an elaborate gravitational dance that profoundly affects any planetary systems attempting to form around either star. Their elliptical orbit brings them close enough every 80 years to gravitationally perturb objects throughout both stellar vicinities. This periodic disruption creates conditions fundamentally hostile to the stable planetary orbits that life requires. Orbital mechanics operates according to precise mathematical laws that admit no exceptions. Two massive bodies orbiting each other create a complex gravitational field that varies with time as their positions change. Any third body attempting to orbit one of the stars must contend with periodic gravitational tugs from the other star. These perturbations accumulate over time, gradually shifting orbital parameters until stable configurations become unstable and formerly circular orbits become eccentric ellipses. James Webb observations focused on detecting the thermal signatures and reflected light from any planets orbiting Alpha Centauri A and B. The telescope's infrared sensitivity should reveal Earth-sized worlds at distances corresponding to habitable zones around these sun-like stars. Preliminary analysis from earlier observatories had suggested possible planetary candidates requiring confirmation. The extended observation campaign produced results that transformed our understanding of this binary system's planetary potential. The observational techniques employed by James Webb exploit fundamental physics that governs how planets reveal themselves across interstellar distances. Every object with temperature above absolute zero emits thermal radiation at wavelengths determined by its temperature. Earth-sized planets in habitable zones radiate most strongly in the mid-infrared, precisely the wavelengths where James Webb's instruments achieve maximum sensitivity. A planet at Earth-like temperatures glows faintly, but detectably against the cold background of space. Separating planetary signals from overwhelming stellar glare requires sophisticated coronagraphic techniques that block the central star while allowing light from surrounding regions to reach the detectors. James Webb's coronagraphs can suppress starlight by factors of thousands, revealing faint companions that would otherwise be lost in the stellar glare. The Alpha Centauri observations pushed these instruments to their limits, searching for thermal signatures at angular separations corresponding to habitable zone distances. The observation campaign spanned multiple epochs over 18 months, allowing astronomers to track any orbital motion that would confirm planetary nature rather than background contamination. A genuine planet orbiting Alpha Centauri A or B would shift position measurably over this time frame, following the predictable arc of Keplerian motion. Background objects would remain stationary relative to the stellar pair. This temporal baseline provided crucial discrimination between real planetary detections and instrumental artifacts or distant background sources. The data revealed clear evidence of disrupted circumstellar material around both stars. When stars form from collapsing clouds of gas and dust, leftover material settles into rotating disks from which planets eventually coalesce. These protoplanetary disks contain the raw ingredients for building worlds: silicate dust that becomes rocky cores, ice particles that deliver water, gas that forms atmospheres or accumulates into giant planets. The architecture of our solar system reflects the orderly processes that occurred in the disk surrounding our young sun 4.5 billion years ago. Alpha Centauri A and B show spectral signatures, indicating their protoplanetary disks suffered catastrophic disruption early in the system's history. The gravitational interaction between the two stars during their closest approaches would have stirred and scattered disk material, rather than allowing it to settle into stable orbits. Computer simulations of binary star formation demonstrate that tight binary pairs regularly destroy or severely truncate the planet, forming disks around their component stars. The physics of this disruption follows inevitably from gravitational dynamics. When two stars approach within tens of astronomical units, their combined gravitational field creates tidal forces that stretch and distort any disk material orbiting either star. Particles that were following circular orbits around one star suddenly feel strong pulls from the other star. Their orbits become eccentric, carrying them into regions where they collide with other particles at high velocities. These collisions do not build larger objects, but rather grind existing material into smaller fragments. The destruction sequence unfolds over millions of years in a cascade of increasingly violent interactions. Initially, the binary perturbations merely elongate particle orbits without causing immediate collisions. Dust grains and pebbles that had been drifting peacefully on nearly circular paths find themselves on elliptical trajectories that cross the orbits of their neighbours. The first collisions occur at modest velocities, perhaps a few meters per second, producing some fragmentation but also some sticking as particles merge into larger aggregates. But the perturbations continue with each binary orbit. Eccentricities grow higher. Orbital inclinations tilt out of the original disk plane. Particles that survived the first round of collisions now face crossing velocities of tens of meters per second. At these speeds, silicate grains shatter rather than stick. The aggregates that had begun forming are pulverized back into their constituent particles. The constructive phase of planet building reverses into destructive grinding. The violence escalates further as the most eccentric particles achieve crossing velocities of hundreds of meters per second. Impacts at these speeds vaporize portions of the colliding bodies, converting solid material into expanding clouds of gas and microscopic debris. The energy released in these hypervelocity collisions heats the surrounding material, driving off volatile compounds that might otherwise have contributed to planetary atmospheres or oceans. The disk transforms from a nursery of forming worlds into a demolition zone where nothing can survive. The distance between Alpha Centauri A and B falls into a particularly problematic range for planet formation. Stars separated by only a few astronomical units can possess stable circumstellar disks that extend modestly outward before reaching the gravitational boundary where the companion star dominates. Stars separated by hundreds of astronomical units barely interact with each other's planetary systems, allowing full-size disks to form and evolve around each star independently. The 11 to 36 astronomical unit separation of Alpha Centauri A and B creates what planetary scientists call the disruption zone, a configuration that maximizes interference with planet formation while still allowing the stars to orbit relatively close together. Numerical simulations, conducted by research teams worldwide, have explored planet formation in Alpha Centauri-type binary systems. The results consistently show that disk material in the regions corresponding to habitable zones experiences particularly intense disruption. Material closer to either star, well inside the habitable zone, might survive the gravitational stirring. Material far from both stars, well outside the habitable zone, also remains relatively undisturbed. But the zones where temperatures would permit liquid water receive the worst of the gravitational chaos. This brings us back to the real loss embedded in these observations. The same proximity that made Alpha Centauri A and B attractive targets for astronomical study is precisely what doomed their planet-forming potential. We can see these stars easily because they orbit close together, bright enough to appear as one of the most prominent points in the southern sky. That closeness, however, created gravitational conditions that prevented the formation of stable planetary systems during the crucial early epochs when worlds are built from circumstellar debris. James Webb detected faint infrared excess around Alpha Centauri, consistent with a sparse debris disk containing remnant material from the failed planet formation process. Unlike the rich planet-forming disks that surrounded our Sun 4.5 billion years ago, this disk contains only scattered remnants. The total mass of detectable debris amounts to less than 1% of the material that built the terrestrial planets in our solar system. Whatever worlds might have begun forming around Alpha Centauri were likely destroyed or ejected before they could reach significant size. The infrared signature of this debris disk tells a story written in wavelengths of light rather than words. Coal dust farther out emits at longer wavelengths. The spectral shape of the emission reveals the spatial distribution of material throughout the system. James Webb's multi-wavelength observations mapped this distribution with unprecedented detail, revealing a disk that is both sparse and spatially confined compared to the debris disks around single stars of similar age. The inner edge of the Alpha Centauri. A debris disk lies farther from the star than the habitable zone. Material that once occupied the region where liquid water temperatures prevail has been cleared away entirely. The disk begins at distances corresponding to the outer solar system, roughly where the asteroid belt would be if scaled to Alpha Centauri A's luminosity. Inside this boundary, observations detect essentially nothing but empty space and the star itself. This inner clearing testifies to billions of years of gravitational processing. Material that once filled the inner system was either ground to dust, fine enough to be blown away by stellar radiation pressure, or perturbed onto trajectories that caused it to fall into the star or be ejected from the system. The habitable zone has been swept clean of the raw materials that planets require. Even if gravitational conditions somehow permitted stable orbits in this region, nothing remains from which to build worlds. The debris disk represents the wreckage of planet formation rather than its ongoing success. Spectroscopic analysis reveals that this material consists primarily of silicate dust, similar to the asteroids in our solar system. The particle sizes indicate collisional grinding rather than accretional growth. Bodies that tried to form were smashed apart by gravitational perturbations that increased collision velocities beyond the threshold for constructive accumulation. The situation around Alpha Centauri b appears even more severe. This smaller, cooler star would need planets orbiting relatively close to receive adequate warmth for liquid water. Observations show minimal circumstellar material in the regions where habitable planets would need to exist. The habitable zone around Alpha Centauri b lies between roughly half an astronomical unit and 1.1 astronomical units from the star. At these distances, the gravitational perturbations from Alpha Centauri A would destabilize planetary orbits on timescales of millions of years, far shorter than the billions of years required for life to emerge and evolve. Numerical simulations of the Alpha Centauri b habitable zone reveal the mechanism of this destabilization. When the binary stars approach their closest separation of 11 astronomical units, their gravitational interaction reaches maximum intensity. Planets orbiting Alpha Centauri b at habitable zone distances experience periodic velocity kicks that gradually increase their orbital eccentricity. Over millions of years, these accumulated perturbations transform initially circular orbits into highly elliptical paths that carry planets alternately too close and too far from their star for stable climate conditions. Eventually, orbital eccentricities grow large enough that planets approach gravitational boundaries where they become vulnerable to ejection or collision. Some simulated planets are flung out of the system entirely, becoming rogue worlds drifting through interstellar space. Others spiral inward and plunge into their parent stars. A few might survive in special orbital configurations, but these survivors occupy orbits too close or too far from their stars for habitable temperatures. Some researchers had hoped that planets might survive in special orbital configurations called resonances, where gravitational perturbations average out over time rather than accumulating destructively. Resonant orbits exist in our solar system, with Jupiter's moons providing well-studied examples. If planets around Alpha Centauri A or B could establish themselves in similar resonances, they might persist despite the binary companion's gravitational influence. The mathematics of orbital resonances involves ratios between orbital periods that lock objects into synchronized dance patterns. When two bodies orbit with periods in simple integer ratios like 2:1 or 3:2, their gravitational interactions repeat in regular cycles that can stabilize rather than destabilize their orbits. Jupiter's moons, Io, Europa, and Ganymede, maintain a 4:2:1 resonance that has persisted for billions of years despite their continuous gravitational interaction. Translating this protective mechanism to the Alpha Centauri system requires identifying orbital radii where resonances with the binary period might occur. Researchers calculated these locations and found that potential resonant orbits lie either too close to the stars for habitable temperatures or too far for adequate warmth. No resonant configuration places a planet in the temperature range where liquid water could exist. Even if resonant habitable orbits existed in principle, reaching them would require fine-tuned initial conditions that planet formation processes cannot provide. Planets do not form precisely at resonant locations. They migrate toward resonances through gravitational interactions with disk material during formation. But the Alpha Centauri disks were disrupted before such migration could occur. The resonant safe harbors, if they exist at all, remain empty because no planets survived long enough to reach them. The James Webb observations searched for evidence of planets in such protected orbits. The search found nothing substantial. If resonant planets exist in the Alpha Centauri A and B system, they must be far smaller than Earth, and therefore unlikely to retain the atmospheres and geological activity necessary for habitability. The telescope's sensitivity would detect Earth-sized worlds in any orientation that produced detectable signals. The absence of such detections constrains the possible planetary population severely. The orbital mechanics become even more complex when including Proxima Centauri, the red dwarf companion that completes this triple star system. Proxima orbits the central binary at a distance of roughly 13,000 astronomical units, completing one orbit every 500,000 years. This vast separation means Proxima barely affects the dynamics of Alpha Centauri A and B directly. However, Proxima's presence reveals important information about the system's violent history that has implications for planet formation throughout the stellar family. Current theoretical models suggest that Proxima Centauri was not born alongside Alpha Centauri A and B, but was captured later in the system's evolution. The capture of a passing star requires a close gravitational encounter that transforms the interloper's trajectory from a flyby path to a bound orbit. Such encounters release enormous gravitational energy that must be absorbed by other bodies in the system. The most likely energy sink would have been any existing planetary systems around Alpha Centauri A and B. Picture the cosmic geometry of this capture event unfolding over thousands of years. Proxima Centauri, then a solitary red dwarf wandering through the galaxy, drifted into the gravitational sphere of influence surrounding the Alpha Centauri binary. Its initial trajectory would have carried it past the binary pair and back into interstellar space, but at closest approach, the gravitational interaction extracted just enough kinetic energy to bend its path into a bound orbit. The energy balance of gravitational capture follows strict physical law. Proxima arrived with more kinetic energy than a bound orbit permits. That excess energy had to go somewhere. Three-body gravitational interactions can transfer energy between participants, with one body gaining speed while another loses it. Any planets or planetesimals orbiting Alpha Centauri A and B would have served as energy repositories, absorbing Proxima's excess kinetic energy through gravitational interactions that simultaneously destabilize their own orbits. The timescale of capture spans thousands of orbital periods as the three stars settle into their current configuration. During this extended interaction, gravitational perturbations would have swept through the planetary zones of Alpha Centauri A and B repeatedly. Objects on marginally stable orbits, perhaps survivors of the earlier binary disruption, would have been shaken, loose, and scattered. The capture of Proxima Centauri essentially pressure-tested whatever planetary systems remained, and the test proved too severe for any worlds to survive. If this capture scenario is correct, whatever planets might have survived, the binary formation process would have faced additional disruption when Proxima joined the system. The gravitational perturbation from a passing red dwarf would have scattered planets already weakened by the binary interaction. Worlds on marginally stable orbits would have been pushed into chaotic trajectories that led to ejection or collision. The capture event may have delivered the final blow to any remaining planetary formation in the Alpha Centauri system. The evidence for capture comes from analysis of Proxima Centauri's current orbital parameters. Its 13,000 astronomical unit separation and half-million-year orbital period produce gravitational binding energy that seems inconsistent with formation alongside the central binary. Stars that form together from the same molecular cloud typically end up much more tightly bound. Proxima's loose attachment to the system suggests it arrived later, captured during a chance encounter that happened to produce the right velocity and trajectory for gravitational binding. James Webb spectroscopy examined the composition of remnant material around Alpha Centauri A and B, searching for clues about what kinds of planets might have attempted to form. The observations revealed chemical signatures consistent with rocky material similar to the asteroids in our solar system. There is no evidence for the volatile, rich compositions that would indicate water-bearing worlds, or the presence of substantial ice content necessary for delivering oceans to forming planets. This chemical evidence suggests that any solid material remaining around Alpha Centauri A and B baked dry long ago. The repeated gravitational stirring prevented material from settling into cold regions where water ice could persist. Instead, the entire circumstellar environment experienced heating events that drove off volatile compounds. Whatever worlds might have formed from this material would have been dry from birth, lacking the water necessary for surface oceans or even substantial atmospheric humidity. No matter how advanced the technology becomes, these formation deficits cannot be overcome. A planet that forms without water cannot magically acquire oceans later. The delivery of water to early Earth came from water-bearing asteroids and comets that existed in our solar system's outer regions. Alpha Centauri A and B lack comparable reservoirs of volatile, rich material. A world ejected from its star system cannot be returned to stable orbit. The gravitational energy required to recapture an escaped planet exceeds anything that natural processes or conceivable technology could provide. The violence that characterized the Alpha Centauri system during its formative epochs left permanent scars that no subsequent evolution can heal. The raw materials for building habitable worlds were destroyed or scattered before planets could form. The chemical inventory necessary for oceans and atmospheres was driven away by thermal processing during gravitational stirring. The orbital configurations that would permit stable habitable zone residence never established themselves because gravitational perturbations prevented such configurations from persisting. The debris disk around Alpha Centauri A continues to evolve, with material slowly spiraling inward toward the star or being ejected into interstellar space. James Webb will monitor this evolution over coming decades, watching the final remnants of planetary potential disappear. The observations provide a time-lapse view of a star system, cleaning up the wreckage of failed planet formation, sweeping away the evidence of what might have been under different gravitational circumstances. Some astronomers have proposed that planets could form late in a star system's evolution, coalescing from debris after the gravitational environment stabilizes. The Alpha Centauri binary has now completed billions of orbits around their common center of mass. Perhaps conditions have calmed sufficiently for new planet formation to begin. Perhaps material that was too dispersed to form planets initially might now accumulate constructively. James Webb observations directly test this hypothesis by searching for evidence of ongoing accretion or coalescing planetesimals. The search found no such evidence. The debris material shows spectral signatures consistent with grinding and destruction rather than accumulation and growth. Particles collide and fragment into smaller pieces rather than sticking together to build larger bodies. The gravitational environment remains too disturbed for constructive accumulation even after billions of years of evolution. Late-stage planet formation is not occurring in the Alpha Centauri system. The physics of planetesimal growth requires collision velocities below certain thresholds for particles to stick together rather than shatter apart. In our solar system's protoplanetary disk, collision velocities average roughly 1 meter per second or less in most regions. slow enough for dust grains to adhere upon contact and gradually build larger objects. The gravitational stirring in the Alpha Centauri system elevates collision velocities to tens or hundreds of meters per second, fast enough that impacts destroy rather than construct. This velocity enhancement results from the eccentricity pumping caused by the binary companion. As material orbiting one star feels periodic gravitational tugs from the other star, orbital eccentricities increase. Higher eccentricity means that objects at the same average distance from the star move at different speeds when they cross each other's paths. The velocity difference during crossings determines collision outcomes. Elevated crossing velocities produce destructive collisions. The mathematics of this process follows inexorably from celestial mechanics. Two-body motion produces stable elliptical orbits that persist indefinitely in the absence of perturbations. Three-body motion, with two stars and a planetesimal, produces chaotic trajectories that resist simple prediction. The chaotic element means that some planetesimals will experience close approaches to the companion star that dramatically alter their orbits, while others will avoid such encounters and maintain more stable paths. The overall effect is to spread the orbital parameters of the planetesimal population, increasing encounter velocities when different populations cross. Computer simulations tracking millions of virtual particles through billions of virtual years consistently reproduce this destructive outcome. Regardless of initial conditions, disk material in the habitable zone regions of Alpha Centauri A and B evolves toward fragmentation rather than accumulation. The simulations show planetesimals forming briefly during periods of relative calm, then being destroyed during the next close approach between the binary stars. No simulation run has produced Earth-sized planets in stable habitable zone orbits around either star. The timescale for habitability is another crucial factor that the Alpha Centauri system cannot provide. Life on Earth required several 100 million years to emerge from prebiotic chemistry, and another 3 billion years to produce complex multicellular organisms. Intelligent life appeared only in the last few million years of this 4 billion year evolutionary trajectory. Any habitable planet must maintain stable conditions over comparable timescales for life to have reasonable probability of emerging and evolving. The orbital stability calculations for hypothetical Alpha Centauri planets show that even marginally stable orbits persist for only millions of years before gravitational perturbations accumulate to the point of ejection or collision. This timescale is 3 orders of magnitude shorter than the time life required to emerge on Earth. Even if a habitable planet somehow formed in this system, it would be destroyed long before life could arise. The gravitational clock runs too fast for biology. All of this still fails because the underlying gravitational architecture cannot be changed. Alpha Centauri A and B will continue orbiting each other forever, their mutual perturbations preventing stable planetary orbits throughout their habitable zones. No future technological intervention could stabilize a planet against these continuous gravitational disturbances. You cannot turn off gravity. You cannot eliminate the companion star. The system is inherently unsuitable for hosting worlds where life might emerge and persist. The comprehensive picture emerging from James Webb observations reveals a stellar system fundamentally hostile to planet formation. The central binary configuration disrupted protoplanetary disks during the crucial early formation period. The possible capture of Proxima Centauri delivered additional gravitational chaos. The chemical composition of remaining material lacks the water ice necessary for building habitable worlds. Ongoing debris evolution shows destruction rather than construction. Every indicator points toward the same conclusion. The implications extend beyond the specific case of Alpha Centauri to the broader question of planetary formation in binary star systems. Roughly half of all Sun-like stars exist in binary or multiple star configurations. If the Alpha Centauri case proves representative, then half of all potential planetary hosts may be fundamentally unsuitable for forming habitable worlds. The galaxy contains fewer promising targets for the search for life than optimistic estimates suggested. James Webb observations of other binary systems throughout its operational lifetime reinforce rather than contradict the Alpha Centauri findings. The telescope has examined dozens of binary pairs with separations similar to Alpha Centauri A and B, searching for evidence of planetary systems or substantial debris disks. The pattern that emerges from this broader survey matches what Alpha Centauri demonstrates in detail. Binaries with separations between 10 and 50 astronomical units consistently show truncated or absent circumstellar material in habitable zone regions. The few binary systems that do host confirmed planets exhibit very different architectures than Alpha Centauri. Some contain extremely tight binaries, where the two stars orbit so close together that they function gravitationally as a single object, allowing planets to orbit the pair at safe distances. Others feature extremely wide separations, where each star maintains an essentially independent planetary system beyond the gravitational reach of its companion. The intermediate separation range that Alpha Centauri occupies appears to be a genuine dead zone for planet formation. This observational pattern validates decades of theoretical predictions that binary dynamics would constrain planetary formation. The theoretical framework preceded the observations by many years, but without direct measurement, skeptics could question whether nature might find pathways around the mathematical constraints. James Webb has now closed that loophole. The theoretical predictions accurately describe what actually happens in binary star systems. Alpha Centauri is not an anomaly, but a representative example of a common phenomenon. Yet even if planets somehow formed and survived in the Alpha Centauri system, they would still face the radiation challenges that doom Proxima b. The next chapter examines what James Webb revealed about the stellar winds and particle bombardment that create a radiation prison around every world in this system, completing the case for why our nearest stellar neighbours offer no sanctuary for life. Imagine standing on a world where the sky never darkens and the ground never cools. One face of the planet roasts under eternal daylight, while the opposite hemisphere freezes in perpetual night. The boundary between these extremes, a narrow twilight zone circling the globe, experiences constant atmospheric turbulence as temperature differentials drive hurricane-force winds. Storms rage perpetually along this terminator, carrying heat from the blazing day side toward the frozen night side, in a desperate atmospheric attempt to equalize temperatures that can never truly balance. This is the fate of tidally locked worlds, planets that orbit so close to their stars that gravitational forces have synchronized their rotation and revolution. Just as our moon always shows the same face to Earth, tidally locked planets always show the same face to their stars. The day side bakes under continuous stellar radiation. The night side never receives direct starlight at all. The climate extremes this creates would challenge even robust planetary atmospheres. Proxima b almost certainly exists in this configuration. A planet orbiting just 7.5 million kilometers from its star experiences enormous tidal forces that gradually slow its rotation until one hemisphere permanently faces the stellar surface. The gravitational gradient across the planet's diameter creates differential forces that act as a brake on rotation. Over millions of years, this braking effect operates inexorably until the planet reaches tidal lock. The timescale for tidal locking depends on orbital distance and planetary properties. But for worlds in the habitable zones of red dwarfs, the process completes within hundreds of millions of years at most. Proxima b has orbited its star for billions of years. Tidal locking is not a possibility for this world, but a certainty. The planet turned one face permanently toward Proxima Centauri, long before complex chemistry could have organized itself into anything resembling life. James Webb observations cannot directly image the surface of Proxima b. The planet is far too small and distant to resolve as anything more than a point of light blending with its star's glare. But spectroscopic analysis of how starlight interacts with the planet during its orbit reveals information about surface temperature distribution. The techniques involve measuring tiny variations in the combined light of star and planet as the planet orbits, teasing out planetary signatures from the overwhelming stellar signal. The data confirms extreme temperature differentials consistent with tidal locking. The day side reaches temperatures where rock would glow red hot, perhaps 1,300 Kelvin or higher depending on surface composition. The night side drops toward temperatures where even carbon dioxide would freeze solid, approaching 100 Kelvin or lower in the absence of any heat transport mechanism. The difference between these extremes exceeds 1,000 degrees, far larger than any temperature differential found on Earth. The habitable zone concept assumes planets can distribute stellar energy across their surfaces through atmospheric circulation. Hot air rises on the day side, flows toward the night side, cools and descends, then returns to the day side to repeat the cycle. This circulation moderates temperature extremes, preventing the day side from becoming too hot and the night side from becoming too cold. With sufficient atmospheric mass and appropriate composition, even tidally locked planets might maintain liquid water across significant portions of their surfaces. Proxima b lacks the atmosphere necessary for this distribution mechanism to operate. The James Webb spectroscopy that found no atmospheric signatures also means no atmospheric circulation. Heat cannot be transported from day side to night side through air currents that do not exist. The temperature extremes persist unmoderated, with each hemisphere experiencing conditions determined entirely by direct exposure, or lack thereof, to stellar radiation. The thermal extremes created by tidal locking generate their own atmospheric destruction mechanisms, even for planets that initially possess substantial atmospheres. Gases migrate from hot regions toward cold regions following pressure gradients. On a tidally locked planet without sufficient heat distribution, atmospheric gases would flow from the hot day side toward the cold night side. Upon reaching the frigid night side, these gases would cool and potentially condense, depositing onto the surface as frost or ice. This process, called atmospheric collapse, can strip a planet of its gaseous envelope through purely thermal means. Water vapor condenses into ice on the night side. Carbon dioxide freezes into dry ice deposits. Even nitrogen, which remains gaseous at remarkably low temperatures, might eventually accumulate in cold traps if nightside temperatures drop low enough. The atmosphere gradually transfers from gaseous form surrounding the planet to solid form deposited on the nightside surface. Atmospheric collapse alone would doom habitability, but Proxima b faces this mechanism in combination with stellar radiation that prevents any atmospheric recovery. Even if volcanic outgassing released new gases into the atmosphere, those gases would either be stripped by stellar winds and flares or would migrate to the night side and freeze out. The combination of tidal locking and active stellar bombardment creates redundant destruction mechanisms that ensure atmospheric loss cannot be reversed. But tidal locking represents only one aspect of the radiation prison that confines every world in the Alpha Centauri system. James Webb's instruments detected the stellar wind emanating from all three stars in the system. Streams of charged particles accelerated outward by magnetic forces. These particle flows carry material from stellar surfaces into interplanetary space, creating invisible rivers of plasma that wash over any planets in their path. Our Sun produces a stellar wind that carries roughly 1 million tons of material into space every second. This may sound like an enormous amount, but spread across the vast volume of the solar system, the density remains quite low. By the time solar wind reaches Earth's orbit, its pressure has diminished to levels that our magnetic field can deflect around the planet. This deflection creates the magnetosphere, a protective bubble that shields our atmosphere from direct particle bombardment. The magnetosphere does not stop all solar wind particles. Some leak through at the magnetic poles, creating the aurora borealis and aurora australis. But the vast majority of incoming particles are channeled around the planet, rather than impacting the atmosphere directly. Without this magnetic shield, the solar wind would gradually strip away atmospheric gases through a process called sputtering, where incoming particles knock atmospheric molecules to escape velocity. Mars provides a cautionary example of what happens without magnetic protection. Mars once possessed a thicker atmosphere and possibly liquid surface water, but Mars lacks a global magnetic field to deflect the solar wind. Over billions of years, the solar wind stripped away most of Mars's atmosphere, transforming a potentially habitable world into the cold desert we observe today. The process was gradual but inexorable, demonstrating the long-term consequences of unshielded stellar wind exposure. Proxima Centauri produces a stellar wind that makes the solar wind seem like a gentle breeze by comparison. James Webb spectroscopy measured the intensity of particle emission from this red dwarf and found wind densities hundreds of times greater than solar levels at equivalent distances from the respective stars. A planet orbiting in Proxima Centauri's habitable zone experiences particle bombardment that would overwhelm any plausible planetary magnetic field. The enhanced stellar wind results from the same magnetic activity that produces Proxima Centauri's frequent flares. The churning convective interior that generates intense magnetic fields also accelerates particles to high velocities. These particles stream outward along magnetic field lines, creating a stellar wind of exceptional density and energy. The wind varies in intensity as magnetic configurations change, but even baseline conditions far exceed what planets in our solar system experience. Even Earth's robust magnetosphere would fail to protect an atmosphere against such intense particle flux. Earth's magnetic field deflects the solar wind because the field's magnetic pressure exceeds the solar wind's dynamic pressure at a distance of several Earth radii from the planet. This standoff distance defines the magnetopause, the boundary between the magnetosphere and the solar wind. Inside this boundary, Earth's magnetic field dominates. Outside, the solar wind dominates. If the solar wind were hundreds of times more intense, the standoff distance would shrink dramatically. The magnetopause would be pushed much closer to Earth's surface, perhaps even below the top of the atmosphere. Atmospheric molecules would find themselves exposed directly to particle bombardment rather than protected by the magnetic field. The stripping process that transformed Mars would operate on Earth despite our magnetic field. This brings us back to the real loss revealed by these observations. The absence of atmospheric signatures from Proxima b is not mysterious. It represents the predictable outcome of known physical processes operating over billions of years. The planet formed with whatever atmosphere its original composition provided, then lost that atmosphere to stellar wind erosion because it lacked the magnetic protection necessary for atmospheric retention under such intense bombardment. The radiation prison has no visible walls, only consequences that accumulate until nothing remains. The magnetosphere problem becomes even more severe when considering how tidal locking affects planetary magnetic field generation. Earth's magnetic field is generated by convection currents in our planet's liquid iron core, a process called the geodynamo. Hot material rises from the inner core boundary, flows through the liquid outer core, releases heat to the overlying mantle, then sinks back down to repeat the cycle. This convection creates electrical currents that generate and maintain the magnetic field. The geodynamo requires rotation to organize the convective motions into patterns that produce coherent magnetic fields. The Coriolis effect, the same phenomenon that causes hurricanes to rotate, influences the flow patterns in Earth's liquid core. The resulting magnetic field depends critically on how planetary rotation interacts with core dynamics. Tidally locked planets rotate extremely slowly, by definition, completing one rotation per orbital period. For Proxima b, this means one rotation every 11.2 Earth days. Compare this to Earth's rotation period of 24 hours. Proxima b rotates roughly 11 times more slowly than Earth. The Coriolis effect on this slowly rotating world would be proportionally weaker, reducing its ability to organize core convection into magnetic field generating patterns. Numerical models of planetary dynamos suggest that such slow rotation severely weakens or entirely prevents magnetic field generation. The critical rotation rate below which dynamos fail depends on core size, composition, and thermal state, but most models indicate that tidally locked planets in habitable zones of red dwarfs fall below this threshold. A tidally locked planet likely possesses no significant magnetic field to protect its atmosphere from stellar wind bombardment. Even the most sophisticated technology imaginable cannot solve these fundamental physics problems. Creating an artificial magnetic field around a planet would require electrical currents of almost unimaginable magnitude, sustained indefinitely against the constant pressure of stellar wind trying to push the field back toward the planetary surface. The energy requirements would exceed anything any civilization could plausibly provide for geological timescales. Atmospheric replenishment might theoretically compensate for ongoing losses, but the rates involved make this impossible. Replacing losses would require importing gases from other sources at rates exceeding volcanic outgassing by many orders of magnitude. Where would such gas come from? Other planets in the system face the same stripping processes. Material from outside the system would need to be transported across interstellar distances at enormous energy cost. Shielding surfaces from radiation through physical barriers represents another theoretical approach that fails upon examination. Any surface colony would need to be buried deep underground, abandoning any pretense of surface habitability. Underground habitation might protect occupants from radiation, but it does not make a planet habitable in any meaningful sense. You are simply living in a hole on a dead world, rather than living on the surface of a dead world. James Webb also detected evidence of extreme ultraviolet radiation environments around all 3 Alpha Centauri stars. Ultraviolet light carries enough energy to break chemical bonds in atmospheric molecules, a process called photolysis. Photolysis dissociates water into hydrogen and oxygen, splits carbon dioxide into carbon monoxide and oxygen, and destroys more complex molecules entirely. The process operates continuously whenever stellar ultraviolet radiation reaches atmospheric molecules. On Earth, photolysis occurs primarily in the upper atmosphere, where ultraviolet light first encounters atmospheric gases. Ozone in the stratosphere absorbs most incoming ultraviolet before it can reach the lower atmosphere and surface. The ozone itself is produced by photolysis of oxygen molecules, creating a self-maintaining shield that protects the troposphere below. This photochemical balance took billions of years to establish and requires continuous oxygen production by photosynthetic organisms to maintain. Without an ozone layer, ultraviolet radiation penetrates to the surface and destroys organic molecules directly. Early Earth lacked an ozone layer because oxygen was not yet abundant in the atmosphere. Life originated in ocean depths, where water provided protection from surface ultraviolet exposure. Only after photosynthesis had produced enough oxygen for ozone formation could life colonize exposed surface environments, a transition that required billions of years of biological evolution. Proxima b cannot replicate this protective pathway because it lacks the atmosphere necessary for ozone formation or surface liquid water to provide alternative protection. Ultraviolet radiation from Proxima Centauri reaches the planetary surface at full intensity, destroying any organic molecules exposed to it. The radiation intensity during stellar flares far exceeds even the baseline levels, creating periodic sterilization events that would eliminate any surface life that somehow managed to exist between flares. All of this still fails because the radiation sources cannot be turned off or avoided. Stellar activity will continue for billions of years. Stellar winds will continue flowing outward as long as nuclear fusion operates in stellar cores. Ultraviolet radiation will continue breaking atmospheric bonds as long as stars shine. The prison has no exit because the bars are made of fundamental physics rather than material obstacles that could be removed or circumvented. Alpha Centauri A and B present less extreme ultraviolet environments than Proxima Centauri, but their combined radiation output still poses challenges for atmospheric retention over geological timescales. James Webb spectroscopy measured chromospheric activity levels for both stars, finding periodic enhancements associated with stellar cycles similar to our Sun's 11-year sunspot cycle. During activity maxima, ultraviolet output increases significantly, accelerating photolysis and atmospheric erosion for any planets that might orbit these stars. The particle environment around Alpha Centauri A and B creates additional complications beyond what individual Sun-like stars would produce. Both stars generate stellar winds comparable to or exceeding solar levels. but the binary orbital configuration creates complex wind interaction regions where particles from both stars collide and compress. These interaction zones contain enhanced particle densities and magnetic field strengths that would intensify erosion processes for any planets unfortunate enough to pass through them. Computer simulations of stellar wind interactions in binary systems reveal chaotic time variations in particle flux at planetary distances. A planet orbiting either Alpha Centauri A or B would periodically pass through regions where the stellar winds from both stars compress against each other. During these passages, particle densities might spike by orders of magnitude above baseline conditions. The unpredictable timing of these bombardment events would prevent any long-term atmospheric accumulation. The comprehensive radiation environment of the Alpha Centauri system leaves no refuge for planetary atmospheres. Proxima Centauri produces extreme flares, intense ultraviolet, and dense stellar winds that would strip any atmosphere within its habitable zone. Alpha Centauri A and B produce more moderate but still destructive radiation, complicated by binary interactions that create variable bombardment intensities. Every configuration that permits liquid water temperatures also subjects planets to atmospheric destruction mechanisms. The energy budget of atmospheric escape provides a quantitative framework for understanding this destruction. An atmospheric molecule gains escape velocity when it acquires enough kinetic energy to overcome the planet's gravitational binding. Molecules at the top of our atmosphere occasionally achieve such velocities through random thermal motion. But the rate of escape remains modest because our temperature is relatively low and our gravity relatively strong. Stellar radiation accelerates atmospheric escape through multiple mechanisms that James Webb observations have quantified. Direct photodissociation breaks molecules apart, and the resulting atomic fragments are lighter and easier to accelerate to escape velocity. Stellar wind particles impact atmospheric molecules and transfer momentum directly, knocking them upward. Extreme ultraviolet radiation heats the upper atmosphere, increasing the fraction of molecules with sufficient thermal velocity to escape. Each mechanism operates continuously, and their combined effect determines the atmospheric lifetime. For Proxima b, calculations show that an Earth-like atmosphere would be stripped away in roughly 100 million years, far shorter than the billions of years the planet has existed. A thicker atmosphere would last somewhat longer, but would still vanish on geological timescales. The only atmospheres that could persist would be so thick and heavy that surface conditions would become uninhabitable through different mechanisms, excessive pressure and temperature. There exists no atmospheric configuration that allows both long-term persistence and surface habitability. The ultraviolet component of stellar radiation deserves particular attention because of its effects on prebiotic chemistry. Ultraviolet photons carry enough energy to break chemical bonds in organic molecules, dissociating compounds necessary for the emergence of life. The same ultraviolet radiation that sterilizes hospital equipment would sterilize any planetary surface exposed to Proxima Centauri's output. Laboratory experiments demonstrate that amino acids, nucleotides, and other biological precursors decompose within hours under ultraviolet intensities far lower than Proxima b experiences continuously. Some researchers have proposed that subsurface environments might provide refuge from surface radiation, just as deep ocean environments may have sheltered early life on Earth. James Webb observations undermine this hopeful scenario through measurements of penetrating radiation that quantify what theoretical models had predicted. High-energy particles from stellar flares can penetrate meters of rock before their energy is absorbed. The protection afforded by burial diminishes rapidly as the overlying material thins, and environments deep enough to provide adequate shielding lack the energy sources and chemical flows necessary to sustain biological processes. The timeline of atmospheric destruction also matters for any origin of life scenario. Life on Earth required approximately 500 million years to emerge after the planet formed, and this estimate may be generous given uncertainties in dating the earliest fossils. The prebiotic chemistry that preceded living cells required stable conditions for complex molecules to accumulate and interact over geological timescales. Atmospheric stripping that operates on timescales of tens of millions of years would erase the chemical foundations of life faster than biology could bootstrap itself into existence. Consider the molecular oxygen that accumulates in atmospheres as a byproduct of photosynthesis. Earth's atmosphere remained essentially oxygen-free for the first 2 billion years of life's existence. Only after cyanobacteria invented oxygenic photosynthesis and spent hundreds of millions of years accumulating oxygen did our atmosphere become oxidizing. This great oxygenation event fundamentally transformed Earth's surface chemistry and enabled the evolution of complex multicellular life. No such transformation could occur on a world whose atmosphere is stripped away before photosynthesis even evolves. The water necessary for biology faces equally severe challenges in the Alpha Centauri radiation environment. As with ice radiolysis on the surface, ultraviolet photons dissociate water molecules, and the lightweight hydrogen atoms escape to space permanently. This photolysis-driven hydrogen escape has operated on every rocky world in our solar system, including Earth. Our planet retains its water only because atmospheric chemistry captures and recycles most of the freed hydrogen before it can escape. Planets lacking substantial atmospheres cannot perform this hydrogen recycling. Every water molecule exposed to stellar ultraviolet radiation faces permanent destruction through photolysis, followed by hydrogen escape. The timescale for complete ocean loss depends on stellar ultraviolet output and planetary properties, but calculations for Proxima b suggest that an Earth-sized ocean would be lost within hundreds of millions of years. The planet has existed for nearly 5 billion years, leaving ample time for complete desiccation even if it formed with abundant water. The stellar wind carries additional threats beyond atmospheric erosion. High-energy particles from stellar flares include protons accelerated to relativistic velocities that can penetrate deeply into planetary surfaces. These particles produce secondary radiation as they interact with surface materials, creating cascades of ionizing particles that spread the radiation damage far beyond the initial impact site. Surface mineralogy records the cumulative effects of this bombardment through radiation-induced chemical changes that persist over geological timescales. Spectroscopic observations of planetary surfaces reveal the signatures of space weathering produced by stellar wind bombardment. Iron-bearing minerals oxidize under particle radiation, changing their spectral properties in characteristic ways. Organic compounds darken and polymerize into refractory materials that no longer participate in prebiotic chemistry. Ice deposits sublimate preferentially along radiation damage tracks, accelerating volatile loss. Every exposed surface in the Alpha Centauri system bears the chemical scars of billions of years of radiation processing. The cumulative effects of radiation damage extend beyond chemistry to crystalline structure itself. Energetic particles displace atoms from their normal lattice positions, creating defects that accumulate over time. Heavily irradiated materials become amorphous, losing the ordered crystalline structure that characterizes most minerals. This radiation damage affects not just surface layers, but penetrates to depths of centimeters or meters depending on particle energies. Any geological record preserved in rocks would be progressively degraded by ongoing radiation bombardment. The accumulated evidence leaves no pathway to habitability. Every mechanism that might protect planetary habitability fails under the conditions James Webb has measured. Atmospheres cannot persist against stellar wind erosion. Magnetic fields cannot deflect the intense particle bombardment. Oceans cannot survive photolytic destruction over geological timescales. Subsurface refugia cannot escape penetrating radiation while remaining connected to necessary energy sources. The radiation prison has no exits. The stellar activity cycles that modulate radiation intensity offer no reprieve. Proxima Centauri shows no evidence of extended quiet periods when its output might diminish to levels compatible with atmospheric retention. Its fully convective interior generates magnetic activity through mechanisms that operate continuously rather than cycling, as they do in stars like our Sun. The 11-year solar cycle that produces periodic variations in solar output has no analogue in red dwarf stellar physics. The bombardment continues without interruption for billions of years. Alpha Centauri A and B exhibit activity cycles more similar to our Sun, with periods of higher and lower magnetic activity that modulate their radiation output. During activity minima, their ultraviolet and particle radiation might decrease by factors of several compared to activity maxima. But even minimum conditions exceed what Earth experiences during solar maximum. The binary stars are intrinsically more active than our Sun, perhaps because of their gravitational interaction, or perhaps because of subtle differences in stellar structure that remain poorly understood. The magnetic field question deserves deeper examination because magnetic protection represents Earth's primary defense against stellar wind erosion. Earth's field extends thousands of kilometers into space, deflecting charged particles around the planet rather than allowing them to impact the atmosphere directly. Without this protection, the solar wind would strip our atmosphere over billions of years, as happened to Mars when its dynamo shut down roughly 4 billion years ago. Generating a planetary magnetic field requires planetary rotation fast enough to organize core convection through the Coriolis effect. Tidally locked planets fail this requirement almost by definition. Their extremely slow rotation produces minimal Coriolis effect, preventing the organized helical convection that generates dipolar magnetic fields. Some numerical models suggest that very slowly rotating planets might generate weak multipolar fields rather than strong dipolar fields. But multipolar configurations provide far less protection against stellar wind, with field lines that loop back to the surface rather than deflecting particles around the planet. Even if a tidally locked planet somehow maintained a dipolar magnetic field comparable to Earth's, the intense stellar wind at Proxima Centauri would overwhelm it. The pressure balance between magnetic field and stellar wind determines the magnetopore's distance. Earth's magnetopause lies roughly 10 Earth radii from the planet's center under typical solar wind conditions. The same magnetic field facing Proxima Centauri's wind would be compressed to roughly 1 Earth radius or less, inside the planet's atmosphere. Magnetic protection would be meaningless. The radiation prison confining every world in the Alpha Centauri system operates through multiple redundant mechanisms. Any one mechanism might be survivable through fortunate combinations of planetary properties. A strong magnetic field might deflect stellar wind particles. A thick atmosphere might absorb flare radiation. Geological activity might replenish atmospheric losses. But facing all mechanisms simultaneously leaves no escape route. The redundancy ensures that habitability is essentially impossible, regardless of specific planetary characteristics. James Webb observations quantified these mechanisms with unprecedented precision, transforming qualitative concerns into measured certainties. Scientists can now calculate atmospheric loss rates for specific conditions, rather than simply speculating about their magnitude. The numbers confirm what pessimists had long suspected. Planets in the habitable zones of the Alpha Centauri system face radiation environments that would destroy any Earth-like atmosphere within millions of years, a geological eye blink compared to the billions of years required for life to emerge and evolve. The implications extend to how scientists must interpret habitable zone designations throughout the galaxy. A planet orbiting within the temperature range for liquid water has cleared only the lowest bar for potential habitability. Temperature alone does not determine whether a world can support life. Radiation environment, magnetic field strength, atmospheric composition, geological activity, and stellar stability all must align favorably for a world to genuinely support biological processes. James Webb observations of Alpha Centauri demonstrate how rarely these conditions coincide, even in systems that initially appeared promising. Every radio telescope on Earth could be aimed at Alpha Centauri for a century and receive nothing but stellar noise. No signals will emerge from these nearest stars because no one exists there to transmit them. The worlds that orbit in zones where life might theoretically exist are bombarded, stripped, frozen, and baked into sterility, James Webb has shown us that the cosmic house next door is not merely empty but uninhabitable, not merely quiet but dead. The implications of this finding extend far beyond one particular star system to reshape our understanding of where life might exist throughout the universe. For decades, astronomers operated under an assumption that made the search for extraterrestrial life seem manageable. If planets formed commonly around most stars, and if habitable zones existed around most of those stars, then the galaxy should contain billions of potentially life-bearing worlds. Statistical arguments suggested that even if life emerged rarely, the sheer number of chances should produce abundant cosmic biology. The nearest examples should be close enough for detection with sufficiently sensitive instruments. Alpha Centauri represented the closest and most accessible test of this optimistic framework. That test has failed comprehensively. The failure carries weight precisely because Alpha Centauri seemed so promising. The system contains 3 stars, spanning the most common stellar types in the galaxy. Proxima Centauri exemplifies the red dwarfs that comprise roughly 70% of all stars in the Milky Way. Alpha Centauri A and B represent the Sun-like stars that hosted the only confirmed example of life anywhere in the universe. If planets suitable for life cannot exist in this diverse nearby laboratory, the prospects for finding them elsewhere diminish considerably. The statistical implications ripple outward from Alpha Centauri to affect estimates of habitable worlds throughout the galaxy. Every optimistic calculation assumed that nearby habitable zone planets would be common. Finding the nearest stellar system fundamentally hostile to habitability forces revision of these calculations. The correction factors may be large, reducing estimates of galactic habitable worlds from billions to millions or even fewer. Red dwarf stars deserve particular scrutiny in light of the Alpha Centauri findings. These small, cool stars outnumber all other stellar types combined. If you selected a random star from the Milky Way, the odds favour drawing a red dwarf by roughly 3 to 1 over all other types combined. Their longevity exceeds Sun-like stars by factors of hundreds or thousands, providing vastly more time for life to emerge and evolve. A civilization arising around a red dwarf would have trillions of years to develop rather than the mere billions available around stars like our Sun. This abundance and persistence made red dwarfs attractive targets for the search for life. Some researchers argued that red dwarf planets should dominate any cosmic census of inhabited worlds simply because red dwarfs dominate the stellar population. If habitable worlds exist around red dwarfs at rates even modestly lower than around Sun-like stars, the sheer number of red dwarfs would still produce more total habitable worlds. The galaxy might be filled with life clustered around dim red stellar furnaces rather than bright yellow stars like our Sun. James Webb observations of Proxima Centauri revealed that this optimistic view fails catastrophically. The same stellar characteristics that produce red dwarf longevity also produce sustained violent activity that destroys planetary habitability. Fully convective interiors generate powerful magnetic fields that drive continuous flare activity throughout the star's lifetime. The magnetic dynamo that powers this activity shows no signs of diminishing with stellar age. Old red dwarfs remain as violent as young ones. Compact habitable zones require planets to orbit close enough for tidal locking to occur rapidly and for stellar wind bombardment to reach maximum intensity. The warmth that makes these regions potentially habitable comes packaged with radiation that makes them certainly deadly. You cannot receive enough heat for liquid water without also receiving enough radiation to strip your atmosphere. The very properties that define the habitable zone around red dwarfs also define a kill zone that destroys habitability prerequisites. Extrapolating from Proxima Centauri to red dwarfs generally requires assessing whether this nearby star represents typical behavior for its stellar class. If Proxima Centauri were anomalously active, the Alpha Centauri results might not apply broadly. Perhaps most red dwarfs behave more calmly, with Proxima representing an unfortunate outlier that happens to be nearest to Earth. James Webb has observed dozens of other red dwarfs throughout its operational lifetime and found similar activity levels across the population. The violent behavior is not anomalous but characteristic. Red dwarf flare rates, stellar wind densities, and ultraviolet emission levels cluster around values comparable to Proxima Centauri rather than distributed across a wide range that might include calm examples. The nearest red dwarf is typical of its class. This finding effectively eliminates 70% of all stars from consideration as potential hosts for habitable worlds. The most numerous stellar type in the galaxy almost certainly cannot support life as we understand it. Whatever life exists elsewhere must arise around the minority of stars that behave more gently than red dwarfs. The pool of candidates has shrunk dramatically based on a single critical class of observations. Sun-like stars initially seem to escape the harsh verdict applied to red dwarfs. Alpha Centauri A and B produce less extreme radiation than their red dwarf companion. Their habitable zones lie at comfortable distances where tidal locking is not inevitable. A planet orbiting either of these stars at Earth-equivalent distances would receive stable warmth without the bombardment that afflicts Proxima b. Perhaps these larger, calmer stars provide the stability that life requires. Yet the Alpha Centauri observations demonstrated that stellar type alone does not determine habitability. The binary configuration of A and B prevented stable planet formation throughout their habitable zones. Whatever worlds might have begun forming were scattered or destroyed by gravitational perturbations from the companion star. The system lacks the architectural stability necessary for planets to form, persist, and provide long-term homes for biological evolution. Roughly half of all Sun-like stars exist in binary or multiple star configurations. The Alpha Centauri result suggests that many of these systems share similar formation deficits that prevent habitable planet development. Not all binary configurations are equally disruptive, but the Alpha Centauri case demonstrates that binaries with separations in the tens of astronomical units create especially hostile conditions for planet formation in habitable zones. This orbital range turns out to be common among binary star systems. Surveys of binary populations show that separations cluster around values similar to Alpha Centauri A and B, rather than being distributed uniformly across all possible configurations. The specific arrangement that maximizes planet formation disruption occurs frequently throughout the galaxy. Half of all Sun-like stars may be unsuitable hosts for habitable worlds simply because they have companions. The implications compound when considering that single stars may not be inherently superior hosts for habitable planets either. Stars that form in isolation still face their own challenges during early evolution. Interactions with passing stars during formation in dense stellar nurseries could have perturbed planetary orbits. Supernova explosions from nearby massive stars could have sterilized early planetary surfaces with intense radiation. Galactic cosmic rays continuously bombard planets that lack strong magnetic shielding, regardless of stellar properties. Single stars may offer better odds than binaries, but better odds do not guarantee success. The conditions necessary for habitability require favorable outcomes across multiple independent variables. Stellar type must be appropriate. System architecture must permit stable orbits. Planet formation must produce worlds of suitable size and composition. Geological processes must maintain atmospheric and climate stability over billions of years. Each requirement filters out candidates, and the combination of all requirements may leave very few survivors. This brings us back to the real loss that the Alpha Centauri observations quantify. The galaxy contains roughly 400 billion stars. Optimistic calculations once suggested that billions of Earth-like planets might orbit in habitable zones throughout this stellar population. Some estimates exceeded 10 billion potentially habitable worlds in the Milky Way alone. These numbers fueled hope that life might be common, that intelligent civilizations might exist in abundance, that contact with extraterrestrial beings might be achievable within human technological capabilities. James Webb data forces revision of these estimates downward by significant factors. Most red dwarfs are hostile to habitability. Many Sun-like stars occupy disruptive binary configurations. The remainder face numerous challenges that could prevent habitability through various mechanisms. Accounting for these filters reduces the estimated population of habitable worlds from billions to far smaller numbers. The galaxy may contain thousands or millions of truly habitable planets, rather than the billions that optimists projected. The Fermi paradox asks why we have detected no evidence of extraterrestrial intelligence, despite the apparent abundance of potential habitats in the galaxy. The paradox has puzzled scientists since Enrico Fermi first posed the question in 1950. Various explanations have been proposed, ranging from the difficulty of interstellar travel to the self-destructive tendencies of advanced civilizations. Perhaps intelligent species inevitably destroy themselves through war or environmental collapse. Perhaps interstellar travel is fundamentally impractical, regardless of technological advancement. Perhaps advanced civilizations choose isolation or exist in forms we cannot recognize or detect. The Alpha Centauri findings suggest a simpler and perhaps more disturbing resolution to the paradox. Habitable worlds may be far rarer than previously assumed, making intelligent civilizations correspondingly uncommon. If conditions suitable for life exist only on a small fraction of planets in a small fraction of star systems, then the emergence of intelligence becomes a correspondingly rare event. The galaxy might contain only a handful of technological civilizations at any given time, separated by distances so vast that contact becomes essentially impossible. The Drake equation provides a framework for estimating the number of communicating civilizations in the galaxy. The equation multiplies several factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per planetary system, the fraction of habitable planets where life emerges, the fraction of life-bearing worlds where intelligence evolves, the fraction of intelligent species that develop detectable technology, and the average lifetime of such civilizations. The product of these factors yields an estimate of the number of civilizations we might hope to detect. Most factors in the Drake equation have become better constrained through astronomical observations over recent decades. Star formation rates are well measured. The fraction of stars with planets appears to approach unity based on exoplanet surveys, but the fraction of planets that are truly habitable remains deeply uncertain, and the Alpha Centauri observations suggest this fraction may be far smaller than optimistic estimates assumed. Revising the Drake equation with Alpha Centauri, informed estimates produces dramatically different results. If 70% of stars are eliminated because they are red dwarfs with hostile radiation environments, and half of the remaining stars are eliminated because they occupy disruptive binary configurations, then only 15% of stars even potentially host habitable worlds. Further reductions for inadequate planetary properties, unstable orbits, and unfavorable evolutionary histories might leave fewer than 1% of stars as viable candidates. 1% of 400 billion stars still yields 4 billion potential systems, which might seem like an enormous number. But the additional factors in the Drake equation compound these restrictions. If life emerges on only 1 in a million habitable worlds, and intelligence evolves on only 1 in a million life-bearing worlds, and technological civilization develops in only 1 in 1,000 intelligent species, the final count shrinks to numbers measured in single digits rather than billions. Such calculations are speculative, depending on factors we cannot measure directly, but the direction of revision is clear. Every new constraint on habitability reduces the estimated number of inhabited worlds. The Alpha Centauri observations provide quantitative justification for restrictive assumptions that pessimists advocated but could not prove. If habitable planets exist only around the small fraction of stars that combine favorable stellar type, singleton configuration, stable orbital architecture, appropriate planetary composition, and fortunate evolutionary history, then the galaxy might contain only thousands or tens of thousands of such worlds rather than billions. Life arising on these rare oases would be separated by vast distances, perhaps thousands or tens of thousands of light-years, rather than the mere 4 light-years that separate us from Alpha Centauri. Communication across such distances becomes effectively impossible through any known physical mechanism. Radio signals would require tens of thousands of years for round-trip exchanges. A message sent today would not receive a response until civilizations that sent it had experienced thousands of generations of change. The civilization receiving a response might bear no relationship to the one that sent the original query. Meaningful dialogue requires exchange rates compatible with the lifespans of the participants. Physical travel would require even longer timescales using any propulsion technology consistent with known physics. Spacecraft traveling at 1% the speed of light would need 100,000 years to cross 10,000 light-years. Faster travel requires proportionally more energy, with relativistic speeds demanding energy investments that scale toward infinity as you approach light speed. No civilization could afford the energy costs of rapid interstellar travel across distances measured in thousands of light-years. No matter how advanced the technology becomes, fundamental physics constrains what is achievable. Faster-than-light communication violates causality according to Einstein's relativity theory, creating paradoxes involving effects preceding causes. Faster-than-light travel faces the same fundamental barrier, requiring either violation of physical law or exploitation of phenomena like wormholes that may not exist or may not be traversable. These are not engineering challenges awaiting clever solutions, but mathematical consequences of space-time geometry that cannot be circumvented. Civilizations separated by thousands of light-years exist in effectively separate universes. They can observe each other's ancient light, seeing how the other appeared thousands of years ago, but they cannot exchange meaningful information on timescales relevant to either party. They cannot visit each other, they cannot influence each other's development. Each civilization develops in isolation, unaware of the others, unable to benefit from their knowledge or suffer from their interference. The silence surrounding Earth acquires new meaning in this context. We have searched for extraterrestrial signals for over 6 decades, using radio telescopes of increasing sensitivity and sophistication. The search has encompassed millions of star systems across multiple wavelength ranges, using detection algorithms capable of finding signals far weaker than anything human technology produces. We have found nothing but natural phenomena and our own interference. The Alpha Centauri observations suggest this silence reflects genuine cosmic loneliness rather than technological failure or inadequate search strategies. There may be no signals to detect because there are no nearby civilizations to produce them. The nearest technological species might be thousands of light-years away, too distant for their signals to have reached us yet, too remote for meaningful exchange even if signals eventually arrive. We listen to silence because silence is all there is to hear. The search for extraterrestrial intelligence, known as SETI, began formally in 1960, when astronomer Frank Drake pointed a radio telescope at 2 nearby sun-like stars and listened for artificial signals. Since then, the search has expanded enormously in scope and sensitivity. Modern SETI programs monitor millions of frequencies simultaneously across large portions of the sky. Computers analyze the data for patterns that might indicate artificial origin, distinguishing deliberate transmissions from natural radio sources. The null result, after 6 decades of searching, can be interpreted in multiple ways. Perhaps we are looking in the wrong way, searching frequencies or signal types that alien civilizations do not use. Perhaps civilizations broadcast only briefly before transitioning to communication methods we cannot detect or choosing deliberate silence. Perhaps signals exist but are too weak for current technology. The Alpha Centauri observations suggest a more fundamental explanation. There may be very few civilizations to detect anywhere within signaling range. If habitable worlds are rare, and intelligent life rarer still, then the nearest technological civilization might be hundreds or thousands of light-years away. Signals from such distances would be extremely weak, perhaps below the detection threshold of any instrument we could practically build. The silence reflects not the absence of detection capability, but the absence of nearby sources. This interpretation has profound implications for how we should allocate resources in the search for cosmic companions. The Alpha Centauri observations also affect planning for future interstellar missions. If our nearest stellar neighbours host no habitable worlds, then the first interstellar probes must aim at more distant targets. The breakthrough starshot concept envisioned reaching Alpha Centauri in roughly 20 years at 20% light speed. Reaching more distant targets at the same speed would require proportionally longer mission times. A habitable world around a sun-like singleton star might lie 20 or 30 light-years away, requiring voyage times of 100 to 150 years, even at relativistic velocities. Generations would live and die aboard any crewed vessel attempting such journeys. Uncrewed probes would require mission planners to maintain institutional continuity for centuries to receive results. The interstellar future, already challenging, becomes even more daunting when the nearest viable targets lie not 4 light-years away but 4 or 5 times farther. Every aspect of mission design, from propulsion systems to communication protocols to organizational structures, must be reimagined for longer voyages to more distant destinations. All of this still fails because understanding does not change reality. Alpha Centauri remains sterile regardless of human comprehension. The nearest stellar neighbours will never host life that we might contact or visit. The dreams of interstellar exploration that focused on this nearest system must redirect toward more distant targets, adding decades or centuries to any plausible timeline for leaving our solar system. Humanity's cosmic expansion, if it ever occurs, will prove far more difficult than optimists imagined. The James Webb observations of Alpha Centauri complete a transformation in scientific understanding that began decades ago, with theoretical concerns about red dwarf habitability and binary star-planet formation. What once seemed like pessimism has been confirmed as realism. What once appeared as a promising stellar neighbourhood has been revealed as a collection of dead worlds orbiting violent stars in unstable configurations. The nearest potential destinations for human starships are not destinations at all, but warnings about the hostile universe beyond our solar system. This conclusion carries philosophical weight that transcends its scientific foundations. Humanity arose on one small planet and developed the remarkable ability to understand cosmic processes occurring billions of light-years away. We can detect the chemical compositions of distant worlds through spectroscopic analysis. We can measure the ages of ancient stars by studying their evolutionary stages. We can reconstruct the history of the universe from its earliest moments through analysis of cosmic microwave background radiation. This cognitive capacity represents something genuinely rare in the cosmos. The rarity of our situation confers responsibility as well as privilege. If habitable worlds are scarce and intelligent life even scarcer, then Earth represents something precious beyond ordinary valuation. The only confirmed example of consciousness in the universe exists here, on this pale blue dot, orbiting an ordinary star in an unremarkable region of an average galaxy. Whatever life exists elsewhere is too distant to help us or harm us, too remote to share our discoveries or witness our failures. We are alone with ourselves in ways that earlier generations could not have imagined. James Webb will continue observing the Alpha Centauri system and thousands of other stellar targets over coming decades. Each observation will refine our understanding of where life might exist and what conditions it requires. The data will almost certainly continue restricting, rather than expanding the list of promising targets. Habitability appears to demand a conjunction of favourable circumstances that occurs rarely in a universe governed by indifferent physical processes. Yet this restriction of possibilities need not inspire despair. The same observations that reveal the sterility of Alpha Centauri demonstrate the remarkable nature of Earth's own habitability. Our planet formed around a stable, solitary star that produces relatively gentle radiation. Our magnetic field deflects solar wind particles that would otherwise erode our atmosphere over geological timescales. Our atmosphere filters harmful radiation while permitting visible light necessary for photosynthesis. Our geological activity replenishes atmospheric gases lost to space and recycles nutrients through planetary systems. Each of these circumstances could have been otherwise. Together, They created conditions where life emerged and eventually produced minds capable of understanding their own cosmic context. Earth floats in a cosmic oasis surrounded by deserts of unimaginable extent. Their planets bake under radiation that would destroy any exposed organism within minutes of exposure. Their atmospheres have been stripped away by stellar winds that have blown for billions of years without respite. Their surfaces are either frozen in eternal darkness on tidally locked night sides, or scorched by perpetual stellar glare on locked day sides. Nothing lives there. Nothing has ever lived there. Nothing will ever live there. The silence from Alpha Centauri is not mysterious when understood through the lens of physics and observation. It is the expected outcome of physical processes that operate according to mathematical laws we can describe and predict. James Webb showed us what those processes produce across 4 light-years of cosmic distance. The result is sterile worlds incapable of supporting life, circling stars too violent or systems too chaotic for the stability that biology requires. Humanity will continue searching for signs of life elsewhere in the cosmos. The search will necessarily focus on targets more distant and more difficult to study than Alpha Centauri. Any discovery of extraterrestrial life, should it ever occur, will involve worlds so remote that direct investigation remains impossible for the foreseeable future. We may learn that we are not alone in the universe without ever being able to act meaningfully on that knowledge or establish contact with whatever life exists elsewhere. For now, and perhaps forever, we exist in cosmic isolation, surrounded by stellar neighbours that cannot host the life we hope to find. The nearest stars shine on barren rocks scoured clean of any possibility for biological complexity. The universe extends in every direction, vast beyond human comprehension, filled with wonders that can be observed but never touched by human hands or visited by human spacecraft within any reasonable time frame. James Webb has shown us the truth about our stellar neighbourhood. That truth is harsh but valuable. The philosophical weight of cosmic isolation deserves acknowledgement even as we maintain scientific precision about its foundations. Humanity evolved with the assumption of uniqueness, the sense that our world occupied a special place in creation. Copernicus displaced Earth from the cosmic centre, and subsequent discoveries progressively diminished our apparent significance. The galaxy contains hundreds of billions of stars. The observable universe contains hundreds of billions of galaxies. Earth seemed to shrink toward insignificance against these overwhelming numbers. The search for extraterrestrial life offered a counterbalance to this cosmic humbling. If life existed elsewhere, we might not be so alone after all. The sheer size of the universe seemed to demand that life must have arisen independently on countless worlds. Statistical arguments made cosmic biology seem inevitable rather than miraculous. The question was not whether life existed elsewhere, but how soon we would find it. James Webb observations of Alpha Centauri suggest that cosmic biology may be far rarer than those statistical arguments implied. The nearest stars prove hostile to life in ways that apply broadly across stellar populations. Red dwarfs are too violent. Many sun-like stars exist in disruptive binary configurations. The fraction of stars capable of hosting habitable worlds shrinks dramatically when observational constraints replace optimistic assumptions. This finding does not eliminate the possibility of extraterrestrial life. The universe contains such vast numbers of stars that even severely reduced probabilities might produce life elsewhere. But distant life offers no companionship to isolated humans. Civilizations separated by thousands of light years cannot communicate meaningfully or influence each other's development. We may share the cosmos with other conscious beings while remaining effectively alone, isolated islands of awareness in an ocean of stellar nuclear fires. The rarity of habitable worlds, if confirmed by ongoing observations, would make Earth something more precious than earlier generations imagined. Our planet would not be one habitable world among billions, but one among perhaps thousands or millions across the entire galaxy. The casual assumption that we could ruin this world and move to another would collapse entirely. There may be nowhere else to go. No backup planet waiting to receive refugees from environmental catastrophe. This perspective transforms environmental ethics from a local concern to a cosmic imperative. If technological civilizations typically destroy their homeworlds before developing interstellar capabilities, then the explanation for cosmic silence becomes tragically clear. We may be approaching the filter that eliminates most would-be starfaring species. The Alpha Centauri observations suggest we cannot escape that filter by fleeing to nearby stars. We must pass through it here, on this planet, by learning to sustain the conditions that make our world habitable. We know now that reaching toward the nearest stars means reaching toward emptiness. Whatever future humanity builds among the stars will not begin at Alpha Centauri. Our first steps beyond the solar system must aim at destinations far more distant, requiring technologies far more advanced, operating on timescales far longer than the dreams that focused on our nearest neighbors. The cosmic neighborhood is not what we hoped, but knowledge of truth, however disappointing, serves better than comfortable illusions. The golden mirrors of James Webb will continue collecting ancient photons from across the cosmos for years to come. Each observation adds to human knowledge about a universe that existed long before Earth formed and will persist long after our sun dies. We are temporary observers of eternal processes, brief sparks of consciousness in an overwhelmingly unconscious cosmos. The Alpha Centauri observations remind us of this perspective, revealing that even our nearest neighbors are utterly unlike us. Silent worlds that never knew life and never will, orbiting violent stars in chaotic configurations that preclude the stability life requires. This is the disturbing finding that James Webb delivered from humanity's closest stellar neighbor. Not evidence of habitability that might fuel dreams of interstellar expansion. Not promising targets for missions that could launch within human lifetimes. Not companions waiting in the vast cosmic darkness for contact with fellow conscious beings. Instead, confirmation that the universe operates according to physical law rather than human hope. That proximity does not guarantee hospitality, that the stars we dreamed of reaching first have nothing to offer but the cold truth of their eternal sterility. The search continues, the silence persists, and somewhere in the vast reaches of cosmic space, the answer to whether we are alone awaits discovery by future observers, with instruments we cannot yet imagine, seeking signals we cannot yet detect, from civilizations we cannot yet comprehend. Until then, we wait, we listen, we wonder, and we accept that our nearest stellar neighbors offer only the profound silence of worlds that never were and never will be homes for life.